Welcome to this video. This is a video about boundary conditions on standing waves. The goal is for you to understand by the end that any free end of a medium is a location where you must have an antinode, and any fixed end on a medium is a location where you must have a node in order for standing waves to form in the medium. Now, what I'm showing here are not standing waves. These are the opposite. These are both traveling waves. What does it mean for something to be a traveling wave? Well, on the left, we have a sound wave traveling through air. On the right, we have a wave traveling through a string. This wave on the left is called longitudinal because it has compressions. Here's a compressed region, and expansions or rarefactions. Here's a rarefaction. On the right, we have a transverse wave with crests and troughs. But in both cases, those crests and troughs, or compressions and rarefactions, are moving. They're traveling through the medium. The compressions and troughs are moving to the right, and I'm following one now. Here's another one that I'm going to follow, moving to the right. And the compression shape is moving to the right as well. Yeah, see that? To see that compression motion, take a look at this video. We have a compression and a compression, a rarefaction in between. The wave is traveling to the right. The position of compressions and rarefactions changes, and the position here of crests and troughs changes. Let's focus on just the string. If I pause the video, what's the location of a compression? Well, the location is right here, and another location of a compression is right here. But if I let a little time pass, then now the compression has moved to the right. Its location has changed. Here's something very different from what we just saw. Now you're looking at two standing waves. In the case of the string, the compressions are no longer moving, the crests are no longer moving to the right, and neither are the troughs. You always have a crest and compression at this position. So the position doesn't change. And there's another position right here where you get a crest and a trough. And you always have a crest and a trough at this location, and at this location. And at this location right here, this red dot, you never have a crest or a trough. So the position doesn't change. And here, is that true as well? The answer is yes. This red dot is the location of a compression and rarefaction. It's expanded now, it's compressed now. There's an expansion, a compression, a rarefaction, a compression. So there are certain locations on this standing wave where you have compressions and rarefactions. The position of those compressions and rarefactions doesn't change. So what we can say about particles is this, and this is the crucial statement. On a standing wave, the same particles always have the largest oscillation, and the same particles always have zero oscillation. For example, on this standing wave, the particle located right here always has the maximum oscillation, the largest displacements. And the particle located right here also always has the maximum oscillation, the largest displacements. The same goes for the particle located right here. It moves up to this position and down to that maximum position. And there's a fourth as well. On the longitudinal standing wave, this particle has the maximum oscillation. Oops, I drew it too far though. This one right here goes all the way to the left and all the way to the right. It's moving the farthest. And here's another one that has the maximum oscillation. Goes all the way from there over to here. The same particles always have the largest oscillations, and the same particles always have zero oscillation, no displacement at all. Here's how we can describe a standing wave. We can define it according to this property we've just observed. A standing wave is one where some particles always undergo the largest displacement, the ones on the crests and troughs, the ones moving between compression and rarefaction. And then we could also say a standing wave is one where other particles always undergo zero displacement. The particles that undergo the largest displacement, we say that they are located at antinodes, which we've seen that term. The particles that always undergo zero displacement, the location of those we call nodes. Now it's time for us to bring to bear some very important facts about a medium. A medium is just something that a wave travels through. So a medium could be a slinky, or it could be a string, or it could be air. There are lots of different media. Every medium has two boundaries or ends. It's where the medium runs out. No more air, no more string, no more slinky. And there are two types of ends that you can have on a medium. Two types of boundaries. There are fixed boundaries and there are free boundaries. If the boundary is fixed, it means the particle at the end, the last particle, can't move. If the boundary is free, it means that the particle at the edge, that last particle, is free to move. It can move. So on the far right, I've shown an example of a fixed end. The last particle here is clamped down. So if I send a wave through, like that, watch what happens at the last, when the wave reaches this boundary. The last particle in green will not move. See, it doesn't move. Its neighbors move, but it doesn't move. We could also change it to a free end, and here's what that looks like. What we've done is we've taken this last particle, we've connected it to a loop around a pole. So if I send a wave through, right, let's go forward. If I let this wave go through, now the last particle at the edge will go up and down. Okay. There are two important things to notice about fixed ends and free ends. When the end is fixed, okay, the particle at the fixed end does not move. It has zero displacement. See, it didn't move. On the other hand, when the end is free, like this, the particle at the free end, not only does it move, but eventually it will feel the maximum displacement of all the particles on the string. So look at how high this particle goes, how high and how low. It goes really high and really low. The particle at a free end always feels, eventually, the largest displacement. So let's compare what we just learned to some of the original statements we made about standing waves. A standing wave has particles that always feel the maximum displacement. Those are the antinodes. And it also has particles that always feel zero displacement. Those we call nodes. But what we said just now about boundaries was this. At a fixed end, that particle will always feel the maximum displacement, eventually. And at a free end, that particle always feels zero displacement. So, if you want to produce a standing wave on a medium with fixed and free ends, then the fixed end, which feels maximum displacement, will be an antinode. And the free end, which feels zero displacement, will be a node. So let's finally apply this to 4 examples. First example, I've drawn a string. The string is clamped down at one end, and there's a loop which can move up and down a pole at the other end. What are the boundary conditions to form a standing wave on that string? This end is fixed, therefore it must be a node. This end is free, therefore any standing wave will have it as an antinode. The next is a slinky, which has been attached by glue to this wall. This end is not attached to anything. What are the boundary conditions? This is a fixed end because that last slinky coil, that last particle, can't move. That's a node. It's attached to the wall. The wall prevents it from moving forward or backward. And this is a free end because it's not attached to anything, so that's an antinode. What if we take two poles, and between the two there's this rope. The rope is connected to the poles by loops, and the loops can move up and down. What are the boundary conditions here? We have a node at the left because this end is free to move up and down. And we have a node on the right because that end is also free to move up and down. The last is a pipe which contains air. On the left side, there's a wall. The pipe has a wall built in. On the right side, there's no wall. The wall acts like a clamp. Particles are not able to move to the left because there's a wall blocking them from that path. So those particles at the end are fixed in place. The closed end of the pipe is a node. And the open end, those particles are able to oscillate left and right. That's an open, free end, so that's an antinode. In our final example, the 5th we'll do, we have a pipe which is open at both ends. So, on the left side, the air is free, the medium, the air. These last particles are able to move back and forth. They are free to move. That, then, will be a node for any standing wave in the pipe. An antinode, rather. An antinode because they are free. That's a free end. This is another free end, and so that will be the location of an antinode for any standing wave in the pipe.